Okay, welcome back to Tech Leader Stage. Our next panel, the future of computing, AI technologies in the exascale era. Please welcome on stage Stefan Gillich from Intel, Christian Wiebes from NXP Semiconductors, Alan Southall from Infineon, and Tomislav Tipuric from Nefos. Thank you.
All right, welcome to this talk and this panel on the AI technologies in exascale era. I mean, I have some really interesting people together with me. This is my third panel and the last one, so if somebody was on my previous panels, this is the last one. I'm not going to be on the stage anymore. So, we discussed this for a while when we met yesterday and today on the emails. So, Stefan, what is exascale computing, and is it suitable at all for AI?
That's a good question. So a little bit to my history. I have been in high-performance computing, so numerical stuff, for a long time before. Always followed AI, and I'm doing full AI since about 6-7 years at Intel in the Center of Excellence right now. So the exascale kind of notion comes a lot from the HPC world. Basically, there's a so-called top 500 list of the 500 most powerful computers, at least the ones known, who apply for that list. And they have a benchmark which is called LINPACK, and it basically looks at the flops, so the floating point operations capabilities of a system. And yeah, there are 2 systems on this list right now which have an exaflop. And that is where the exascale computing area, I think, really originates from. Does that have a meaning for AI? Yes and no, because the flops, yeah, they say something about the compute capability, but the benchmark is a rather artificial one, right? The LINPACK benchmark, for those who know, they will hopefully agree with me, it's a rather artificial thing, and it basically measures the floating point operations, which are not always the stuff you need for AI, because you reduce the resolution, so you don't need double floating point precision, which you need for numerical computing, for HPC computing. So the requirements are different. On the other hand, the architecture of those systems there, basically they consist of CPUs, some accelerators, GPUs, and so on, right, are basically very similar to an AI system. So these CPUs are multi-purpose, and hence it has a meaning. Those capabilities have a meaning for AI as well.
Okay. Alan, what do you think?
Yeah, I think it's how you define exascale, right? And if you look at exa, the word exa, it's a billion operations. And if you look at floating point, which is what AI requires in terms of matrix operations, I think exascale, in terms of the number of floating point operations you can execute per second in exascale is very, very important, especially for training of AI models. So I see it as highly relevant to AI.
Cool. So when we are at the point of defining terms, can we also describe the typical, I wouldn't say problem, but the typical discussion between GPU and CPU architectures in the context of AI and especially deep learning capabilities, and why is now everybody talking about the GPU being the only thing that you can use for the AI and everything else? What's the reason why GPU became so popular?
Do you want to go first? So
you can continue.
Yeah, so
GPUs,
for me, they're a specialized kind of processing unit. So they're highly specialized in, for example, matrix operations. And I remember, looking at things like systolic arrays. So you have this high parallelism with high throughput of this very specific function. And if you look at AI, it has vast amounts of these matrix operations. So it's essentially in linear algebra, for example, multiplications or other kinds of operations on these highly dimensional spaces. And by having these very specialized parallel processing capabilities, you have this enormous throughput and this, exaflop capability in the future to process these kinds of problems. So if you look at the CPU, it's a very different kind of problem or a different kind of generalized hardware, and parallelizing problems with imperative languages and for high-performance computing is a much more difficult problem as compared to matrix operations.
And you actually mentioned when we were discussing yesterday that that's the part of the whole GPU is the one that's responsible for these kind of operations. So you could technically take the rest out, and that was something that you guys were working on.
Yeah, I mean, you have to look at what AI is. It's basically a lot of AI in its meaning today, let me say it like that, because who knows whether it's changing, but deep learning. What is behind in mathematics is a lot of matrix manipulations, mostly multiplications, and those can be parallelized, as you have said, rather straightforward. So that's what the background is now. If you really look into what you need, it's basically processing cores and matrix manipulation engines which can do that. So if you want to build an architecture for doing deep learning training and heavy inferencing, you can basically build accelerators which are not GPUs, but do a very good job or an excellent job at AI, deep learning, training and inferencing. So that's what we have done with the Intel Gaudi architecture. So this is not a GPU, but it's very competitive to the established platforms, to GPU platforms in terms of the performance you get on what you need to do for deep learning, training, and inferencing. Okay. So that's what you can do. And the other thing, because while we said CPUs are different, yes, but you can also bring in things into CPUs which make this matrix manipulation easier, and we have done that with a technology called advanced matrix extension. So you can enable CPUs to do those things as well.
Yeah, one thing to add, maybe it's just also then coming a little bit more from the edge is then the performance in a given amount of power that you have, right? So if you get with the same power amount that you have in a battery-driven application, for example, to a certain performance that you want, you can rather do that than on a neural network coprocessor than you could do it on the CPU. It, of course, can also calculate this one, but it will be slower on the same power budget that you have.
So when we come to the edge, you're coming, so basically if we are talking about all these exascale things, they're more likely from the perspective of the data center, and we're going to touch base with that with Alan in a second. So when we come to the edge, so basically those smaller little pieces of the puzzle, so that's basically where NXP has the expertise. So can you tell us a little bit about your products that fall into that space?
Yeah, in the end, the edge devices are today almost in all applications also needing ML, machine learning, as one part of AI. And that's regardless whether it's a very tiny microprocessor or whether it's basically one of those application processors which come then with a little bit more compute power. But in the end, there's almost no application at the edge anymore where there's not something where you can really, with machine learning, improve something. Either the quality of service or the quality of the data that you have on a sensor and stuff like that. So that's basically everywhere. That's also why it's for us very important to support then machine learning capabilities on all our products that we offer.
Cool. So Alan, I mean, you guys are designing also those kinds of microcontrollers and all of those semiconductors. So we talked about, everybody's mentioning kind of the trade-off between performance, between energy, and the actual consumption of the compute power. And so, can you tell us a little bit about how do we achieve that on the edge?
Sure. So I think there are two things here. We have the data centers and we have the edge. So in the data centers, we're very active in semiconductor power. So basically supplying the power into these data centers. And if you look at the data centers today, I think they're around 50 megawatts to maybe 150 megawatts in terms of power consumption. And when you start moving towards exascale and very large systems in the future, you're looking at potentially going into a gigawatt. You know, a gigawatt solution that's training a model. That's roughly one power station for a single model that's being trained. And here the power consumption is very, very large. So it's consuming a lot of power. And the kind of products that we build essentially from grid to core, so the actual core running these algorithms, is to essentially increase the efficiency. So the power that is then put into the core so that you can use that power for computation. And then on the edge, what we also do is, for example, in our PSOC Edge products, we basically do a lot of pre-processing at the edge with our sensors, for example, with radar or silicon microphones or CO2 sensors, to then sense the environment and pre-process the data, and using onboard MPUs, so neural processing units, run AI algorithms to offload the cloud, so reduce the amount of energy that's being consumed in the transmission and the computation in the cloud so that you can do it locally. So that's the two areas that we primarily focus on.
Yeah. Yeah, you're describing a real good setup, right? Because what I think is a good strategy to save energy and make it more practical is to say, okay, what kind of AI can I do where the data is? So I don't have to transport the data around a lot. So the edge is very important because a lot of the data comes from the edge. So having an architecture which basically takes the edge as the first thing and tries to do whatever needs and can be done there, and then relies on the data center and the cloud for more sophisticated tasks which need more performance. I think that's a really good architecture to maintain a lot of things like being energy efficient, but also keeping data more local and more private, because that's a requirement as well. Maybe not for machines, but for other data like healthcare data, right? When you have the data of a radiologist in that machine, so you want to do as much as you can, as close to the data, so you don't have to copy the data around so much. Yeah. So that is, I think, a forward-looking architecture, which is done today already.
That's right. And it also strongly depends on your application, of course. You will not everywhere have a neural network coprocessor if it's not needed. If you say you have very slow data from a sensor or temperature, humidity, you name it, then of course, and those changes are very slow, then it's a much more different thing than if you say I have now video data, or I have a machine where I want to have a certain quality control based on pictures of a wafer, for example, where you say I want to really know whether there are scratches and stuff like that, and then I need to really do it with several frames per second or so. So you also need, of course, to adopt your devices to your use case, and then also towards what is the power supply that you have. It's a single isolated sensor that is somewhere, which only is in the range of milliwatts, or it's something where you say you have several watts that you can use to do the application, and you have a certain requirement on the speed and accuracy you need to apply.
That's really, really interesting topic. So there's another interesting topic which we always need to come whenever we are talking about the IT. So Alan, what about security?
Yeah, so security is a really important topic, and again, we have here silicon that supports this. So the optical range that we have. Essentially, there are a number of things you have to do. You have to make sure that you have an environment where you have safe compute, so you're running in a safe environment. That the connectivity is safe, that certificates are safe, you know, that you have certificates in rotation on the device, that you have safe updates, safe boot. So that's incredibly important to secure the edge, to be able to do these computations. When it comes to AI, it becomes a little bit more tricky as well. So one of the techniques that we use is you know, training large models in the cloud and then distilling them down onto the edge. And one of the things you want to make sure is that they're secure. And so some of the things that we're working on is making sure that the actual code that's running the algorithm is trustworthy. So making sure that you have trustworthiness in the AI, that it hasn't been somehow manipulated on the edges, is I think going to be very important moving forward.
Yeah. Also, one point is, okay, we can do a lot with the hardware, obviously, when we are designing these kinds of solutions, but it's not just hardware, there's software component to it.
Yeah,
so we spoke, when we discussed it yesterday a little bit, you mentioned actually, how can we leverage some stuff like GPT language models for example, to actually optimize and help people optimize their code so that it's going to be running better on the chosen platform.
Yeah, let me say something on the principles of software first and then answer that question. Because I think what we were discussing on the hardware side is a choice of hardware, right? Do you have more capable, less capable, depending on the area you want to use it, an AI PC at the edge or in the data center. Those architectures are different. And we need to support it. So the best is to have an open software stack on top of that. So the developers, you out there, don't have to worry which hardware is below, and we can reuse it. So that's very important for us, right? Two things: choice on the hardware side, which we're offering, and openness on the software stack. So that's a principal consideration on the software stack. Now coming to your question, can we use AI to make code better? Yes, you can. There are several things you can do. It starts, first of all, with optimization. So you can use LLMs to basically look into the code and suggest optimizations. And obviously, you can draw this into a bit more automation as well. So it's actually a good tool for developers. And when I developed code a long time ago, that was always the boring stuff, right? Or when you get any kind of things, if you program in C, you get a segmentation fault, right? Okay, go and look for that. If we had the tools which are available today through AI, wonderful, right? So I think it can be used, absolutely. And we're working with startups as Intel, and there's one startup you can visit at our booth who is exactly doing that, using LLMs for code improvement.
Cool.
Maybe one addition on the topic before on the security, because I think especially from the development perspective that's important. I think there are a lot of things, of course, you also need to apply in the machine learning. So you always need to look at also at the edge to see how do you boot. Do you have implemented a secure boot, for example? I can only recommend to do that. And of course, also on the way how you identify nodes in a network, whatever network it is, whatever kind of connectivity setup you have, you need really to make sure you identify, authenticate your devices, and you also secure then the connectivity, and you have to have an update service in order to then, of course, update also against security or other failures or bugs that you have in the system. I think the principles also when using ML, for example, in the edge, are not different, but they are very important, and they are not always taken into consideration in the way we would love to see it, honestly.
But your company also offers a set of tooling. So when we were talking about the tools that are available there, so can you expand a little bit on that?
Yeah, that's also very important. As when you have edge devices, and you said it, there's of course a certain amount of memory that you have, and you don't have more, and there's a certain amount of speed and resources that you have. So, and we offer for example, the EIQ, and the EIQ is an environment where you find then the neural network models on the one hand, and you also can use it in order to do the training of your model. You have then compilers in there, you have libraries in there, and also you have then abstraction layer, hardware abstraction layers, for example, for TensorFlow or for Glow or ARM neural network. So it's really about how do we provide also to the developer something there where he can really then come with his problem and right away go into selecting the right model, training it, testing it, and then say, yes, now my application runs with the performance and in the budget that I wanted to achieve.
Yeah, I think the development tools as well are super important. It's something that we spend a lot of time on as well with Modus Toolbox. You know, the ML models and bringing ML models onto our microcontrollers is very important. But I think there's another important aspect for developers, and that's with the advent of AI, is using to actually develop algorithms themselves. So using it to develop a control algorithm that is in many cases more optimal than what a human could write. Right? So I think this is the potential that we're seeing coming through software, and maybe the advent of software development being augmented through agents that develop code themselves and algorithms.
Cool. So, I mean, we are now kind of like the last third of our panel. So I would like to ask a question. It's a more general question, but Alan, you can start. What the future holds? So obviously we now described where we currently are, what we are currently doing. So basically, I mean, there are many different approaches. There's neuromorphic computing, optical computing, quantum computing. We had a panel this morning about quantum computing. So what do you think is going to be the next thing in this kind of I wouldn't say just exascale compute, but any kind of massive compute?
So if I go to massive scale computing, and I know this sounds maybe not very intuitive, but I think power is going to be one of the major limiting factors. So if you think that the power consumption is growing 10% year over year, and by the end of the decade, these data centers are going to be using about 7% of the global electricity. So that's about the size of India, all of the energy consumed by India. So getting that power into these data centers, getting it into the cores so that they can process that data is going to be very, very important. And I think we're putting a lot of effort into that with new materials like silicon carbide to make sure that that happens. So optimizing that, reducing the carbon footprint. I think that's going to be a big focus. And then going into fiber optics for the interconnect between these chips, I think, is going to be a big aspect as well.
Yeah, I mean, you mentioned a few buzzwords already on that. So I think it's a multi-dimensional problem. Obviously, if we get more AI usage, this will grow the energy consumption, as you have said, and that's what a lot of people have their attention on right now. So you can use efficiencies by this choice of hardware we just discussed. So basically keeping the compute where it's most efficient and most usable. So that is also a part, or you can design your data centers better to be much more efficient. There's a lot of room for improvement there. But you can also go on the chip level, right, and think of different ways to do the compute than we do it today. Today we have the von Neumann architecture. It's around for a long while. It has been proven very efficient. But if you look at what the computer here does, which we carry around all day long, it's pretty efficient in terms of power usage versus output. I hope you will agree. And if you look into that, obviously neural networks are a first step into, yeah, you have neurons there as well, but it's very different. So if you look into neuromorphic computing, very simply spoken, takes this a step further and goes away from some traditional computer architecture without going into too much detail, and has some promises. So our Intel Labs guys have been working on that since quite a long time, and they actually bring out research chips. Loihi 2 is the current one, and they build bigger machines out of that. So if any of you is interested, you can read stuff about it. We don't have the time here. But it's an interesting approach. It's in research, but it shows its practicabilities already, right? So that's one approach. There's certainly others, and we have to work on all of these fronts to make computing more efficient, because we see AI offers a lot of opportunity, people are jumping on it, and we need to make it manageable from a sustainability perspective.
Okay, I mean, Christian, your world was always like that because it's on the edge, so there's no power. Yeah. Those simple things. What's next in that kind of thing?
Yeah, I think to comment on the neuromorphic, I think it still hasn't really shown the promise that it's really at the same time faster and at the same time also going to the same cost. Yeah, or the same even chip area. So in that sense, I'm not yet convinced that this will be the direction. I think scalability is for sure the case. So we will do also different sizes of coprocessors for neural networks, depending on what kind of device we have to address, then really the optimum. And I think it's also a matter of that we are growing together a community. So you might have seen that we also work together with NVIDIA. Now you could say, why NVIDIA? That's your competitor, more or less. But it makes, of course, sense that certain things, pre-trained models, are available that then can be used also on our edge devices. Same holds true with AWS in the sense of how do we make sure that neural networks are trained and developed in the cloud and optimized in the cloud, and then there's a secure way in how we get them down to the target device. And then finally, for sure, and you mentioned it before, it's always good to pre-process data on the edge first and really only send what is needed to be sent. Yeah? So if every data is sent to the cloud and then the inferencing is there and then all the data comes back, that's for sure not helping neither latency nor the power consumption. If you do it on the edge, you can really also save already a lot of data, a lot of bandwidth, and with that, of course, also a lot of power, right? That's very important.
I mean, that's something what people are actually questioning sometimes when they're talking about hybrid cloud, interconnected clouds and everything else. And it's like, okay, but it's not a problem. We can always set up VPN. Well, yeah, you can, but that's encryption and decryption. Your latency is going to suffer due to that fact. Let's better do it on one place. We can easily surround it with anything that we need, and we don't need to use VPN then. So those are the exact same problem, just on a different level. Yeah. And Stefan, I mean, Christian mentioned some of the partners that they are working with. Intel also has a lot of partner programs, I would say, and initiatives.
Yeah, we work a lot with partners. Obviously, we build fundamental technology, hardware, software, and some services around it as well. But that's obviously just foundation. So we work with partners on the hardware side, which are integrating our chips. We work with cloud service providers, and we work with software companies, and with GSIs, you name it, right? The whole ecosystem. But I want to just highlight one thing, because in AI, you see a lot of innovation driven by startups, right? Just look at the scene out there who is doing stuff, a lot of startups involved. So we have a startup program which is called Liftoff. Again, as you're interested, we have actually 2 or 3, don't remember exactly, of our Liftoff partners presenting at our booth. One of them were Turing Tech, the guys who do that code improvement by using Gen AI for that. And there's a few other examples on visual AI. So that is a program I'd like to highlight. Obviously, we have programs for all the other partners we're working with as well, and ad hoc working together. So I think in general, independent of our company, I think it's important that people work together. And for that, it's always good, I said it before, to have an open software environment which enables innovation. So that is very important for us.
Cool. We have a little bit of time for a question from the audience.
So thank you, everyone. So far, we do not have any questions from our remote audience. So the remote audience, if you like to, now is the perfect time to ask a question. Otherwise, does the audience here in the room have questions? Yes.
Can you bring the mic? This is going to be interesting.
Hello, everyone. My question is, what do you think is the future for decentralized or distributed AI, or centralized AI, or the hybrid in regard to the energy consumption?
Okay, I heard.
So I think the question, I didn't hear it very well, but I think the ask was...
Gotta repeat.
The future is for distributed AI, which means AI on the edge mainly, and the update, for example, for the central model on the cloud. It will be better for centralized AI in regard to energy and power consumption. And if so, it is hybrid, how it will be to compromise between the two, or the connection between the two.
Yeah,
Thank you.
so distributed computing, so this is actually where I originally come from. It's a very complex problem. I think you're going to have much more edge-based AI. I think that's going to happen. I think the reason for that is, again, is energy and then doing the computation locally where it's required, where the data is created. If you have very high throughput in Hertz kind of area, you want to process that data locally and not be transferring it into the cloud for processing. So where you have high volumes of data, it's best to process at the edge. I think there'll always be a hybrid. The problem with distributed computing is always security, right? How do you trust the individual components? I worked in peer-to-peer computing for a long time, and this was exactly the problem. If you have pure distribution or pure decentralized infrastructure, it's a problem of security. But I think the edge-based compute will come, and it will save energy, and there'll be always this hybrid between edge and central.
Yeah, I would say it's already happening today because if you look into various areas, manufacturing, healthcare, there's this distribution already between what things which are done at the edge, so where the data is created, be it a machine or visual sensors and stuff, and you can draw it up to automotive, right? It's the same thing. You need to do some compute in the car, right? You can't bring back everything to the cloud and bring it there for latency reasons alone, right? And a massive of data, right? So that's no question. I think the hybrid architecture is already working. And then it depends on the use case where you actually do most of your compute and obviously the compute requirements you have. Can you do it on the edge? Which part can you do it on the edge? And which is better done centrally is depending on the actual application.
But that's kind of what I have a feeling that our industry is constantly going through. You know, we started with mainframes, then we had client-server architecture, then we have peer-to-peer, then we have cloud, then now we have cloud at the edge. So we are always somewhere in the middle trying to figure out, and probably the best option is use what you can for what you need, and not have a general idea, because no problem is actually general. Thank you, guys.
Thank you, thank you. Warm applause. We will be on a break for, brings luck. We'll be on a break for 10 minutes, so stay tuned. Thank you.
Thank you, guys.